Here are the integration by parts formulas that we came up with. There's the one for indefinite integrals and the formula for definite integrals. But writing things out with f and g like this is kind of clumsy. It's excessively verbose. It's hard to remember. It looks more complicated than it is. There's sort of a nicer, more compact way to write this, which is dg dx times dx. Let's call this dv. F, we're going to call this u. So we're just renaming things a little bit. If u is f, then the f on the right-hand side here is, well, that's still u. Sorry, on the left we have integral of u times dv. On the right-hand side, f is still u. G, well, if dv is dg dx times dx, then v is just g, right? Both of these are functions of x, and if you do differentials, you get this. So this g here is just v minus integral of, so right, we said that f is, we called it u. Well, if we take differentials, du, right, f is a function of x, so du is going to be df dx times dx. And so this df dx times dx is df. And g, of course, is v. I'm sorry, not df, du. There we go. So this is a more typical way of writing integration by parts. Integral of u dv is u times v minus integral of v du. You can see it just, integration by parts has the effect of moving the d to the other piece. It works out the same for definite integrals. If you have a definite integral of f times dg dx, then you get, so integral from a to b of u dv equals u times v with your bounds minus integral from a to b of v times du. So same formula, but with bounds. So if you, with a little practice, you can use integration by parts without writing everything out piece by piece like this. You can just use these formulas to write it all out in one line. It does take some practice though, so don't rush to get to that point. Let's look at a couple more examples of how we can use integration by parts. So let's find the antiderivative of x squared times e to the x. So remember, for u, we're looking for something that gets simpler when you differentiate it. That's definitely going to be x squared. So du is 2x dx. For dv, well, the dx is always part of dv, right? The dx part of this integral. If the x squared part went into u, then the e to the x part has to go into dv. And that means v is e to the x. And now we can do our integration by parts formula. So u times v, so x squared e to the x, minus the integral of v, which is e to the x, times du. And du is 2x dx. Okay, so we transformed one integral into another integral. Now we have to ask ourselves, is this new integral any easier to do? Is it any simpler? And the answer is yes. It has a lower power of x, so it feels like we're closer to an answer. Of course, you may not remember what the integral of x e to the x is. We can move this 2 outside and rearrange things to look like integral of x e to the x. I know you may have seen this integral before, but the point of this example is when you use integration by parts to get a new integral, you might have to use any integration trick to evaluate your new integral, including integration by parts again. So we can use integration by parts to evaluate this new integral. So x squared e to the x minus 2 times, and now let's do integration by parts again. But this time u is going to be x, and that means du is just dx. dv is e to the x dx, and so v is e to the x. And so when we write out integration by parts this time, we get u times v, so x e to the x, minus the integral of v, which is e to the x, times du, which is dx. Now finally, this remaining integral is one that we can do immediately without having to use integration by parts again. So we get x squared e to the x minus 2 times x e to the x minus e to the x plus a constant. Okay, and then you can do algebra to simplify this if you want. So let's see, everything has an e to the x except this constant. So the constant will pull out to the back. Everything has an e to the x, so let's factor out e to the x. So we have an x squared, we have minus 2x, and then plus 2. So there we are, we're done. You might say, hey, shouldn't this constant be minus 2 times c? And officially, I guess, but remember, c is an arbitrary constant. If you have an arbitrary constant and you multiply it by minus 2, it's still an arbitrary constant. So here I've just relabeled the old arbitrary constant c with a new label, but the new label is really the old label because it's an arbitrary constant either way, so it doesn't really matter what you call it, c or minus 2c. All right, so this is one variation on using integration by parts, using it twice if you need to, just to sort of grind down the powers of x until they disappear. Let's look at another variation on the theme. So how about finding this definite integral from e to e squared of natural log x? You might have wondered, hey, what is the integral of natural log x? It seems a little bit strange that we haven't figured it out yet. It should have an antiderivative because every continuous function has an antiderivative, but is there actually a formula for it that we could write down? Well, we don't know off the top of our heads what an antiderivative for natural log x is, so we're going to have to use some sort of trick for figuring out this antiderivative. And there's no obvious trick to use. I mean, definitely a u substitution will do us no good because there's not really, the inside is x. And if we did a u substitution with u equals x, we just replace all the x's with u's. That doesn't help. There's no algebra we can do with our integrand because it's just too simple. It's just one single function. There's nothing really to do. So really, the only trick we have left is using integration by parts. And integration by parts, to start out with, you need two pieces that are multiplied. Right? Integration by parts is sort of our integral version of a product rule. And there is no product in here, so we can't even use integration by parts. Oh, but wait, there is a product in here. It's natural log x times dx. So there is a product, so we can use integration by parts. Every integral is a product because if nothing else, it's the integrand times dx. So you always can use integration by parts. The question is whether integration by parts helps or not, whether it actually lets you calculate your integral. So let's see what we could do. So first we have to choose this natural log x. Is that going to be part of u or part of dx? Part of dv. Well, if dv were natural log x dx, to use integration by parts, we would have to know what v is. So we would have to know an antiderivative for natural log x, but that's what we're trying to figure out. So we can't do it that way, because that's sort of circular, right? That brings us back to the original problem. So this natural log x must be part of u. So u is natural log x. That means du is 1 over x dx. So dv, well, there's nothing left in this integral except dx. So dv must be dx. And that means v is just x. So now we can do integration by parts here. So u times v, x times natural log x. And remember, this is a definite integral, so don't forget your bounds, from e to e squared, minus the integral of v du. So v is x, and du is 1 over x dx. So in this remaining integral, this all cancels, and we're just left with 1 as our integrand. Oh, and I forgot my bounds, from e to e squared. So this is x natural log x, and so we're evaluating from e to e squared, minus, and then integral of 1 is just x, again from e to e squared. And now we can evaluate at our bounds. So plugging in e squared, we get e squared times natural log of e squared, which is 2, minus e times natural log of e, which is 1, minus, and now plug in our other bounds. So e squared minus e. And look, this stuff cancels and we get e squared again. Okay, so along the way here, we did find an antiderivative for natural log x dx. Right, we found an antiderivative for natural log. If you look back here, it's x natural log x minus x plus a constant. So if we differentiate, just to check, if we differentiate x natural log x minus x plus a constant, we ought to get back to natural log x. So let's just check, just to be sure. We're going to have to use the product rule for this first piece. So we get derivative of x is 1 times natural log x plus x times the derivative of natural log, which is 1 over x, minus the derivative of x, which is 1, and then the derivative of c is 0. So x times 1 over x is 1, but then 1 minus 1 is 0, and sure enough, we're left with just natural log x. So finally, we filled in the gap of not knowing an antiderivative for natural log x. Of course, now we don't know an antiderivative for x natural log x, but I bet you could come up with a way to figure out a derivative for this one.